in the research network community. A lot of NONs are now happy users of dark fiber networks. 10 gigabit per second speeds is no longer something you can only dream of. So looks like everything is solved, but reality shows that using fat pipes, 10 gigabit per second channels is not as easy as one might think. So this session is about research and development of new optimized high-speed protocols and about making more of standard TCP. We have 3 speakers in this session. The first one is Doug Leet from Maynooth in Ireland, from the Hamilton Institute. His interests include analysis and design of transport layer protocols, particularly in high-speed networks and resource allocation in wireless networks. Please, go ahead. Maybe yes, because it's a bit noisy on the outside.
So Felix introduced by talking about 10, is it not? Is that better? It's on now? Okay, all the technical issues solved then. So the Felix introduced talking about 10 gigabit per second, and I'm going to get to 1 gig here and be quite pleased to be getting there, to be honest. So one of the things I wanted to try and do was often there's been an awful lot of work concentrating on congestion control protocols and changes to the congestion control algorithm itself for high speed. Now I was wanting to branch out a little bit and look at some other aspects, because that's not the only aspect that affects high speed transfers, and also try and give some connection between all the work that's been going on in the research community and in the development community, and how is it finally having an impact in production networks and for actual users and changing the user experience. And so here's an old slide. This slide's 3 years old, and these tests here are 3 years old, and this was in so you can tell from the speed here across the Atlantic was only 1 gig. And so we ran a test with that. Now this actually lower number is probably the most interesting one for this talk. If we take an out-of-the-box Linux stack and just try and run it along here, we'll get 2 to 3 megabits per second across a 1 gig link, and that's pretty bad. And if we tune it to death and do all the right things that we know what to do, we might get you on for 100 times more than that, 50 to 100 times faster. So that's a huge leap by tuning it. And then getting the rest, the other times 5 up to 1 gig is where is what playing with the congestion control algorithm does for you. But there's a separate issue of this huge gain here. What's going on here? In fact, what I would like and what we're used to is that when we take an operating system out of the box, it just works. The network just works. We don't want to have an expert around who can tune it. And so how are we doing? How are we doing for getting there? So there's been quite a few changes to end hosts proposed and actually appearing. Have appeared or are appearing. And so this is a very Linux-focused talk. So there's, of course, there's all these new congestion control algorithms that I'm not really going to talk about today. Maybe Lachlan will talk some more about that. Perhaps if we have time, I'll mention a few things at the end. Instead, I'll talk about these other things here, which are related to other aspects of TCP. So one is a really basic thing about the improved efficient implementation of the network stack. It has to do quite a lot of bookkeeping and there's an overhead, computational overhead, and communication overhead inside the computer at the end host. And we can do things more efficiently without changing the function, and there's gains to be had there. There's things that have been around for a while now, actually, like buffer auto-tuning that I'd like to talk a little bit about, and what impact that may or may not have for a user. And other changes like ABC, which has just appeared in Linux again, and it's a very, very small change in the face of it, and yet its impact could be quite large. And then something slightly more looking ahead. These are all basically, these three here are all basically in the current, the experimental releases of Linux, the 2.6 series. This is something that's been receiving a lot of attention over quite a few years, and so I'll perhaps comment on it. And one of the things that I think I'd like to bring out as well in this talk is that the end hosts don't exist in isolation, and these changes have some links into how the network's configured as well. And there's some interesting points or observations can be made about the interplay between the impact of these changes and whether they're worthwhile or not, and what's happening in the network as well, especially with trends in the network buffer provisioning that you'll all be familiar with. So moving on, a lot of this, the data I'll be showing is from just a little lab test bed. So nice things, so it's just a rack of boxes set up with a single bottleneck and a software router. The nice, so very limited therefore, but still interesting. The nice thing about it, of course, is we can instrument it to death. We know everything that's going on, and everything's very controlled and reproducible, and that's a good first step, and allows me to put up some nice pictures that are very clean. Very clean in the sense of giving good understanding of what's going on, I believe. So all the data from here, pretty much all the data, time history data, is available on the web or our site here. And so there's a database behind that which is searchable, and there's interactive plotting and so on. So I'd encourage you to go look there, because I can only show a tiny part of the data that we've collected, and I'm sure there's lots more interesting things inside the data sets we already have. So here's just repeating maybe that first slide, the things I want to talk about. Let's start with the network stack implementation. And so this is so let's just take that setup, try and run a single flow through it, a tuned up kernel, so we don't have any, it's doing its best that it can, but it's using standard congestion control. And then we'll just increase the line rate and see what happens. How does the throughput rise? Now the throughput should rise according to that red line. It's the only flow on the network. It's provisioned, buffer is provisioned properly. Everything's tuned. But actually with a 266 kernel, so a little bit old now, but it's still the same up to very recently. Actually, the same results would be seen. Look, even after we get to speeds of 100 megs. Now we're not even close to 10 gigs here. Or 1 gig for that matter, is starting to lose throughput. And you can see it's wobbling along, something bad happened there. And up here we're losing roughly something like a factor of 2 in throughput. So what's going on there? That's best case, single flow, everything clean in the lab. And what's up here is that the implementation, actually the computational burden on the end host inside the network stack is too high, and it can't keep up with the processing that's needed, so it's just falling to bits. And so if we poke around and look in at the congestion window time histories for that TCP stack, we can see these big gaps. So this isn't very clear. The red line or purple line there is the congestion window. The green line is how the sequence number is advancing. You see these big flat bits where nothing much happens at all. Look at the time scale here. That was 30 seconds of nothing being transmitted. And what's happening is, if we have a look, this is the time to process an acknowledgement coming back. So these are, once we've had a loss, then we have selective acknowledgements coming back, and there's a bit of bookkeeping of marking the packets that have been sent and which ones have been transmitted and all that stuff. And the average, this is the distribution of times inside the kernel in microseconds to process packets. And this is the line here for 100 megs, or I think that was 250, that you'd need to process it inside in order to keep up with to keep up with the rate the packets are arriving. And you can see there's this huge tail. This is a logarithmic scale. There's very large numbers of ACK packets that just aren't being processed in time. And that causes these big gaps. And so this is now 2615, just this plain kernel now, no changes, apart from having the right TCP buffer settings and all the normal things that one does to tune up a standard stack. And you can see the whole distribution here shifted to the left. And everything's much faster. There's still the odd packet, this acknowledgement packet takes a long time, but this stack, we can actually cope with that because of the buffering internally to the stack. So basically it's able to keep up now, and if we look at the effect on the congestion window time history, so this was just for one particular choice of protocol, congestion control algorithm, we can see everything looks nice and clean now. We've got the acknowledgements, the sequence number is increasing, and everything's looking good again. So you can have a very dramatic difference just by changing the implementation inside the network. the operating system stack, and that's not confined to Linux. Pretty much every other operating system, I understand, has the same problems because it's implementing SAC and selective acknowledgements. And it's only 2.6.15, so very recently, that's been fixed. And so we've checked this, the performance of these recent changes up to 1 gig in 200 milliseconds, because actually it's not just the speed, it's the bandwidth delay product that matters here. So the congestion window size, number of packets in flight. So that's, and it's fine even on regular hardware. We don't need anything too fancy here at all. Just a regular commodity Xeon kit will do the job up to these speeds now. So that feels like good progress. And we're still in the process of checking higher speed operation. Another thing is that was for single flows on these machines. If we look at multiple flows, then I'm not sure what the results will be there. That's also still work in progress. So my first point, maybe picking up on the start of, there's been a lot of talk and a lot of work done on how we might speed up network performance for end users now, not within the network. How can end users actually access the capacity that's available? And here's something which looks very worthwhile. We're getting something like a ×2 increase, and this is already out there in production code, and I'd say that's a pretty good reason to be thinking about upgrading your operating system. Now, so that's the first bit of good news. Ooh. So let me talk about something that's been out there much longer, and that's buffer auto-tuning. That's been inside Web 100 for a long time and is now incorporated into Linux. So what is it? Maybe I'll just quickly recap what the role of why we're interested in buffer auto-tuning. Because I've consistently said that in checking those previous results, we tuned up the stack, and basically what I meant was we'd made sure the buffers were large enough so that everything would run. So what's the role of these are buffers that lie inside the end hosts. So they're the TCP buffers, and they're in the receiver and the sender, and they're pretty fundamental to the operation of the congestion control of TCP. So the TCP is trying to give reliable in-order delivery at the destination. So the receiver, we have to buffer incoming packets so that if they arrive out of order, we wait until the required packets arrive, and then we can deliver packets in order up to the application. So we need to hold on to packets at the receiver until we get them in order. If there's a hole, we have to wait until that hole is filled, and then we can send the packets up. And of course, there's also some need for buffering because of scheduling granularity. At the sender, there's the problems to do with reliable delivery if a packet's lost. So that we have packets that have been sent but not yet acknowledged. If one of those is lost, we have to hold on to that packet and be able to retransmit it. And so we have to hold those in a buffer. So the sender is holding the packets in flight, sent but unacknowledged packets, to allow them to be retransmitted. And again, a little bit of buffering to do with scheduling granularity in the end hosts. So this is the key here, actually. The packets in flight is exactly the bandwidth related to the path properties. It could be something like the bandwidth delay product on a link. And so the size of these buffers is path dependent. The size if we want to make good use of the network capacity, that is. And so if the buffer size is too small, then we just can't send enough packets to fill up the network pipe, and we don't get good utilization. And that was the very first number back on the second slide with the 2 or 3 megabits per second across the Atlantic, because the buffers were too small. So for a 64K kilobyte buffer, which would be sort of largish actually for a standard distribution default settings, then on a 100 millisecond path, we're going to get roughly 2.5 megabits per second. Regardless of the link speed, we could have a 10 gig link, but we won't be able to use it purely because of the buffer. So this is once we've got an efficient network stack implementation that can actually sustain the high speeds, the second thing is we need big enough buffers to fill the pipe and make use of it. And so the benefits of using the right size of buffers are huge, and it's the first thing all the tuning rules say we should do. And it's important to say we need the same sufficient buffering at the source and the destination. At one end alone isn't going to be good enough here. So why don't we just set all the buffers to be huge? Well, the problem is it's tying up physical memory, and if we've got multiple TCP flows running on a machine, each of them is wiring that big chunk of memory potentially. And so we can eat up our physical memory really quickly. So we want to do something a bit cleverer. And so that's the idea of auto-tuning. We set a maximum, but each flow will just grab the amount of buffering that it needs, and so we divide up the available memory across flows. And so this is not my plot. This is out of the original auto-tuning paper, where we've got the congestion window bouncing around, and the buffer size here is keeping some space there. It's roughly twice the congestion window. So are we done? Why don't we? Why don't we now? Since that's now in standard Linux, it's going to the talk is in the next version of Windows and so on. We just need to then set a large maximum for the senders, and the flows will adapt, and we're sorted. So is that going to happen? There's a problem though, which is that now what you've done is you've allowed the end host to be able to fill a big pipe, and the big pipe might not be a bandwidth delay product, maybe because there's a big queue out there. And so this is some data off of a DSL link. And so what's happening here is we're just increasing numbers of FTP flows actually, each with a 64K buffer. And what we see, so that's what the steps are. We're just opening up a new flow. And so I'd draw your attention to the scale here. So this is milliseconds, but we're at 4,000 or so, 3,500 before we gave up. It wasn't stopping. It hadn't bottomed out up there, flattened out up there. So 3.5 seconds of queuing. And that seems to be reasonably common on DSL links and other low-speed connections, wireless, for instance. So if we've got these very large queues, and we've given our end host big enough buffers that they can fill that queue, and they will fill them, because that's what TCP's congestion control will do. It will probe and probe and probe until it gets a loss. So it will fill these queues right up until it gets a loss. And then we've got seconds worth of latency if we're not careful. And if we want our machines to work, my laptop to be able to, I can use it on my DSL connection at home, and I can take it to work, and I can use it on the gig connection there, and it should just work. Then I certainly can't just have a large buffer size and rely on auto-tuning, because that'll work just fine in the office, but it'll be terrible at home if I'm doing anything interactive, if I'm doing web or anything like that. So basically, even though it's there, we're still relying on manual tuning of end hosts, and that seems that's the first unsatisfactory point I'd bring to your attention. There's work needed here. If users actually just to get a plug-and-play experience where they can just take their operating system out of the box and get good performance as they're used to in the past, then this sort of issue has to be dealt with. So there's already been a little bit of progress on that. FreeBSD have their own solution based on that. It's a delay-based kind of idea that tries to get, it's clear that when we have these huge queues that there's plenty of information. If we see a huge queuing delay, we should be able to do something about that. And so this is one attempt at doing that. But I don't think it's a final one, and it's not been widely adopted. So I think there's certainly plenty of scope for, continues to be a bottleneck here in terms of user experience, and there's plenty of scope for more work to be done there. So let me move on to some other things. So ABC see, I'm running out of time. The ABC is appropriate byte counting. So again, it's a very simple idea that traditionally TCP is probing for bandwidth. So what it does is increase the number of packets in flight, one for every, on receiving every C-wind worth of AX. So it's kind of it bootstraps itself up. Now, it's all in terms of counting acknowledgement packets coming back. And what ABC does is it changes it to counting bytes. So that means an acknowledgement packet might actually acknowledge 10 packets rather than just one packet. And so this would change that and be more aggressive. And so it seems like a simple logical change, and this is in the spirit of the original TCP standard, the RFC. But it's a huge impact because delayed ACking is used everywhere. And so essentially it doubles the slope. If this is our sawtooth where we're probing and backing off, this is the congestion window, then basically it doubles the slope of it. And so everything becomes much snappier, and we double the throughput for the same loss. So for this very small change, it's really quite dramatic impact. And this is for standard TCP, but it has a similar effect on all the loss-based ones. So finally, let me just talk. I mentioned about links into twice of network buffers. So there was one issue there about very large buffers being problematic, and then I was having to accommodate that. But here's another. So there's for a long time now, people have been toying with the idea of rate pacing. It's never been seriously rolled out. and it's still, and there's renewed interest in it, and it's worth having a look at, having a think about it. So what is rate pacing? Well, the current strategies have act clocking. After we've received a C-wind's worth of packets, we increase the C-wind and just immediately fire out a new packet, and that's what that blue one is. So it's back to back. After the last act we put up, we tend to generate bursts like this, packet trains. So what ideal rate pacing would do is space those out. So, but the point is, so what we're doing is changing the burst structure. It's very fine grained now. See the time scale here, this is a round trip time, so we're talking a few, maybe tens of milliseconds. So it's very fine grained. And we're changing that fine grained structure of what's happening. So what's the impact? The first question is, well, we expect that to immediately have an impact on router queues, because they're having to deal with those that's exactly the time scales they're dealing with in absorbing bursts. And so that links into some work that's a couple of years old now by people at Stanford, looking at statistical multiplexing. If we have many flows going through a single link, then they don't all back off at once, and so we can perhaps get away with far smaller buffers. And so this, for example, look at the pluses, would be standard TCP for 98% link utilization. We only need a buffer of 50 packets, and this was on a 62 meg link. But it relies on there being very large numbers of flows because something bad's happening down here. And it also depends on other factors I'll just come back to. So the first thing, though, that's important is this isn't just any old link. These have to be links where the queue is doing some work. So, for example, an over-provisioned link in the network core where there is no queuing, where there is virtually no packet loss, this is not relevant. This is relevant to heavily loaded core links that may be due for an upgrade, or edge links where there's aggregation and actually significant amount of packet loss happening. So the first thing is it depends really strongly on the mix, on the traffic mix. So here's the same setup as before, but now we've got some mix of connection sizes, so there's some web traffic in here. And because of the burstiness that slow starts creates, then look at the numbers here. It was 50 before, now the pluses are now more like 300, so we've had a big jump in the level of buffer size just by changing the mix of connection sizes. So there was the previous one down here. So it's not so straightforward to make use of that, but that's kind of known. The questions I was wanting to ask were, well, all of this is for standard TCP. What's the impact of these new congestion control strategies, all of which are more aggressive than standard TCP? Are they going to create more burstiness, prevent using higher queues, prevent us getting away with small queues, and so on? And the second thing is what the impact of operating system changes like rate pacing, which also affect the burst structure. And so here's some experimental data where it's very, very simple but quite interesting, where we take two long-lived TCP flows, 100 meg links, so not fast, just 80 millisecond delay, but the results scale up, actually. And we vary the queue on the bottleneck links as a fraction of the delay bandwidth product. Now, in the delay bandwidth products 1, we're expecting 100%. It's slightly less because of the Ethernet framing costs and so on. So those numbers do match up. Those are the right numbers. And we're doing it for standard TCP and a raft of different proposals, and also a simulation just as a sanity check that there's no surprises in here. So the solid line here is standard TCP. Now, the interesting point here is this knee. When we get to 3% of the balanced delay product, when we try and make the queue lower than that, look at the throughput. So 75% here, in theory says 75% should be what we get, even if there's no queue. If we're, theory being some ideal situation. So we're at 75%, but when we try and make the queue below 3%, it just crashes. The throughput collapses and down to 10% down here. The 10 to 1%. So something interesting is happening here. And notice it's the same point for all these different protocols. It's the same point for scalable and HTTP and high-speed TCP and big. So the different algorithms haven't really affected what's happening here. The exception is fast, which is doing it about 8%. And I'll come back to it. There's good reasons why it's doing that. So what's actually happening, if we look at the loss rate, what we find is that those points, the loss rates are going through the roof. This is logarithmic, right? So it's going from 10 to the minus 6 to 10 to the minus 4. It's going up 2 orders of magnitude. And if we look at the C1 time histories, the measured ones, this is for 3% when things were still okay. So look, here's the two flows, C1 time histories, there's about 400 packets in flight each. And then when we reduce it to 2%, like the C1, we've got far more losses. And it's still, still regular shape TCP. What's happening is there's far more losses, and it's driving down the mean C1 size, the peak C1 size. And then for 1%, we're down to 60 packets. So we're just seeing lots and lots of losses, and it's driving down the throughput. And we can get some understanding of what's causing those losses by looking at the burstiness of the packet stream. So with ACK clocking, delayed ACKing, the first thing to look at is delayed ACKing. So that generates lots of back-to-back packet pairs, because each ACK acknowledges 2 packets, and so we send another 2 out. So it certainly causes more bursts than regular ACKing. And so if we've got all these 2 packet bursts, let's try and be as cautious as we can. Just say that they've got these packet pairs. Then if we look at the numbers here for this bandwidth delay product, the threshold is about 20 packets. So below, when we're down at small numbers, it doesn't. If we're aggregating 2 flows, combining bursts from these, then we're ending up with bursts of size 4, no bother. And we just need a few of those, 2 or 3 of those, and suddenly we're filling these queues and causing all those drops. And actually, the real situation is a little worse than that when you poke around a little bit more and take some more measurements, because, of course, there's end-host scheduling granularity. There's not, when we receive ACK, so each ACK doesn't just generate, the delayed ACK doesn't just generate 2 packet pairs, 1 packet pair being sent out. Because of the fact that there's a delay and there's a few ACKs actually arrive before the end-host responds, it often sends out quite a few packets. So this is the distribution of number of packets ACKed, cumulative distribution. So you can see about 50% of them, the time, it's only 2 packets. But there's a significant amount of the time that we're getting far more than that. So the burstiness is actually far higher than that really conservative analysis would suggest, and that's kind of why things are going through the floor. And we can get some sense of this by looking at 1 millisecond. So at this point, it was 1 millisecond was the scheduling granularity in the end host. So if we send 1,500 byte packets, then at 100 megs, that's 8 packets. At 500 megs, it's 41. At a gig, it's 83. So we can reasonably expect that number of packets, bursts of those sorts of magnitude, to be being generated just purely because of scheduling granularity. And coming back to fast, and then I'll just wrap up after that, we can say something. So fast is pacing for starters, so it's interesting to look at, but also seem to stop. We run into trouble a good bit earlier. And if you think a little bit about what the fast uses, unlike the others, use the delay-based congestion control strategy. And it's trying to maintain, roughly speaking, and I'm sure Lachlan will correct me if I got it wrong, is a standing queue. Each flow will try and maintain a standing queue. And between the two flows, in this case, they'll try and maintain a standing queue of about 20 packets in the queue. So 5% balanced delay product, which is this point here, is 34 packets. So we have to knock off 20 of those because we've got a standing queue. And so the space left for bursts is only about 14, and we're back to the sorts of numbers we were seeing for regular flows. So something very similar is happening here once we correct for what the difference in the congestion control strategy. And the point here is fast here is using rate pacing, but because of the scheduling granularity, the rate pacing is not working finely grained enough to affect the sorts of sizes of bursts we're seeing, and doesn't scale. So there's a summary here, which is that there is a lower threshold on queue size, as far as it's certainly not all our experiments and simulations as well, below which the efficiency collapses. And I use the word collapse intentionally. The efficiency doesn't just drop a small amount; it drops to sub 10% utilization. The threshold is very complicated, so I haven't tried to put some theory under here, because it depends on the mix of flows, the number of flows, the types of them, it changes in time. It's very hard to predict, but we can measure it. It doesn't seem especially sensitive to the congestion control algorithms we're using, so new sorts of congestion control algorithms don't seem to affect it too much with the comment regarding fast. And software rate pacing, which is what we're considering here, really seems to have very limited impact. And we haven't been looking at hardware rate pacing here. But my only comment would be, all we need is a single bursty flow sharing a link to be causing problems for all the flows sharing that link. So we need all of them to have good pacing if it was to have real benefit. And so it seems to me this has some direct implications for switch, if I move towards switch architectures, which have typically very small queues on them. So there's anecdotal evidence on switch LANs, for instance, of burstiness from cross-traffic, hammering throughput. The move towards switched LANs is basically extending that to the wide area, very small queues. So we have to, I think there's a need for some more measurements really to understand better what's going on there. And let me stop there. Thanks, Felix.
Thank you very much. We have room for one or two questions. Harald?
So the traditional received wisdom is that a queue in the middle of the network that is less than one RPT times bandwidth will harm performance. Now, I'm not sure how I read your numbers, but you seem to indicate that a buffer that is less than 3% of the bandwidth delay product will harm performance. That means that I can reduce my buffers by a factor of 30. Is that a correct interpretation?
So that's not got a yes or no answer. So for starters, let me put my plot up again, since you asked a question about what the plot said. So look, this is saying efficiency versus queue size. If I want to get, here's 94% after framing. If I want to get that, I need to have a bandwidth delay product. If I have 10% of the bandwidth, this is a log scale now, 10% bandwidth delay product, I have certainly, so I'm pointing to the bottom line, that's standard TCP. I've certainly sacrificed throughput. I'm now down to something like high 70s. Right? I've lost significant, and that's the received wisdom. The question, and absolutely in keeping with, this is also for small numbers of flows. So this part here is what I'm focusing on. If you try and go to very small queues, then there seems like curious things happen.
So if I can buy twice the bandwidth for what 10% of the queue size, then I'm better off.
10% though.
So if I can, if this is 100 megabits,
Mm-hmm.
and I can make it 200 megabits, if I can be okay with 10% of the buffer size.
Could be.
This is an interesting trade-off.
Yeah. So that's the trade-off. The discussion I've heard in the context of optical networks where buffering is very expensive. Larry.
So, Doug, does this contradict Guido's work, or because the flow counts are so different, does it not really make comparison?
I don't. So it doesn't contradict it. It extends it. So the question is, what's this number here? So what happens is, if we increase the number of flows, things plateau out, the gain stops. Where's that threshold there? That's what it's about. So it's focusing in on what the details of that number, and it depends on the mix of flows. And one of the really important things about one of the real value from doing experimental tests is all these issues about scheduling, granularity, and so on are we just don't know how to simulate those, and they're important.
Last question.
So with the queues you're just talking about now, presumably that's any queue at the end-to-end path, including any queues within the end systems?
So let me get back to, since if I've prepared some of these slides. Where is it? There, that's the queues I mean. So the queues where there's congestion. Congestion as in they're filling up and generating packet drops and providing feedback to TCP. Other queues are, I'm not talking about them.
Okay, thank you. I think we have to stop here and move ahead. Thank you very much, Doug. Our next speaker is Vladimir Smotlacha from JESNet. He is speaking about parallel socket library. Vladimir received his Master of Science degrees in computer science from Czech Technical University and Charles University in Prague. He worked as Unix system programmer and administrator, and since 1996 he's with JESNet. JESNet is the national NRAN of Czechoslovakia. Oh, sorry, Czech Republic. His research interests include monitoring, time synchronization, quality of service, high-speed networks, and communication protocols. don't get the picture, unfortunately.
Good afternoon. Is it okay? Good afternoon. At first, I have to say that I'm not author of the paper and of the PSOC library. The authors are my colleagues Sven Ubik and Martin Čížek. Unfortunately, Martin Čížek is no more with CESNET, and Sven Ubik has vacation this week. So he asked me to give this presentation. The capacity of the available bandwidth of current geographically large network is much higher than several years ago. And it implies that the parameter given as a product of the bandwidth and delay is so high that the throughput of standard TCP flow is limited. There are generally two ways how to solve the problem. The first one, very common, is implementation of some new faster TCP version. There are many of such versions were designed, some of them were implemented. Unfortunately, there is no consensus until now which one is the best, and this better or faster TCP is not yet part of standard system kernels. So there is also another option how to solve it, and it is to split the data stream into some parallel flows and transport these flows by standard TCP. The parallelization can be done on different layers. In case of link layer, it is well known the spanning tree protocol or Cisco Ether channel. There are also some possibilities on network layer. The common feature is that such parallelization is absolutely transparent for any application. However, it should be done by the network designer and network operator. Another possibility is to implement parallelization in application layer, but in this case it means a lot of programming for the application designer, application author, in order to solve further multiplexing and the multiplexing of data. So there is also another one possibility, it is to implement parallelization in transport layer as a parallel sockets. According to analysis of current implementations, there were identified several requirements that should be fulfilled by the parallel socket. At first, it should be easy to introduce parallel sockets into already existing application. Second, the socket has to utilize the available bandwidth of the transport path and to be independent on some changes in available bandwidth. and of course there should be some effective algorithm solving the distribution of data into individual paths, individual flows. The PSOC, the parallel socket library, which I am now describing, was designed in order to fulfill all these requirements. So how PSOC looks? It is based on two communicating threads. The library thread is started by the application, and then the library thread forks off the protocol thread. Various components of these threads communicate via a common platform, common interface platform. The communication is currently implemented by exchange of messages. However, other method can be used too. The picture shows some of the most important messages. There are messages exchanged between the control engine and the peer. There are messages invoked by events on data sockets. There are messages that control the multiplexing module. And one of very important are also messages that update the schedule table, which is shared by the control engine and the data dispatcher. Here is an example of one state of such schedule table. There are three parallel data streams, and let me assume that the demultiplexer just finished reading from stream 0. Then the scheduler reads item from that table, and there is available information that the next portion of data, in this case 1448 bytes, is available in flow number 2. In case there will be no such item, the system should wait until the network delivers another portion of data. Quite similar it is done for writing to the sockets. Very important part of PSOC is the method how data are distributed into parallel streams. It means how the schedule table is filled. There are currently implemented two such algorithms. The first one is called round robin, and it distributes the data equally into all streams. So in case in case of different throughput of streams, the total throughput is done by the stream with minimal throughput. There is also another better algorithm that is called poll-all driver, and in this case data are written into any stream that has enough space in the buffer. So the total throughput is done simply by sum of throughputs of all individual streams. In each TCP is very important issue the sizing of buffers. In standard TCP with single connection, uses buffer for two purposes, mainly two purposes. It is for reassembling of, in case of lost data or reordering of data packets. Another purpose of buffers is also to allow for application some space for application to read or to write data and not to wait every time for the network. It is also well known that general rule for sizing of buffers is done by the product of round trip time and available bandwidth. In case of parallel socket, there is also another new purpose for buffers. Buffers are needed also for reassembling data from different flows, as the throughput of flows is varying and the delay is varying and so on. This slide shows a general formula for estimation of minimal size of receiving buffer for parallel transfer. The formula contains throughputs and delays of individual streams. And mainly it is necessary not just difference between the slowest and the fastest stream. So it is so calculation of according to this formula depends on our estimation or our knowledge about the dynamic behavior of the real communicating paths. The PSOC has been tested in two test beds. The first one was laboratory test bed based on NIST-net system, and the second one was a real network, which is our test bed Checklight. And, here are some results of the testing. These three graphs are from NIST-net testing. The first graph shows the dependence of total throughput on the number of flows and on the size of the window. So we see that even for a very small window, in case of 7 flows, we can reach 80% of theoretical throughput. It is just only for demonstration. Definitely such small window is .2 is of the product is not used in standard network. The second graph is from another configuration of the test. In this case, there were 2 communicating paths with different capacity. The x-axis shows the ratio of capacity of both paths, and we see the difference between the pole driver, this line, and the round robin driver, this path. So it demonstrates the test demonstrates that only for equal capacity of both paths, the round robin driver gives us results as good as the pole driver, which doesn't depend on the capacity of these 2 paths. The last graph is from another configuration. In this case, only 1 path was used, but there were artificially implemented packet losses with the rate 10 to -5, and we see that the 90% of theoretical throughput was reached in case of 6 parallel flows. So for that particular configuration and that particular rate of losses, we need 6 flows. Here is another graph from the testing on check light test bed. In this case, we used two different paths, and into one path was injected some background traffic. The time, here is the time. It is between 0 and 15 seconds, and the background traffic started at second 5 and stopped at second 10. The green line shows the throughput in case of pole-all driver. The red line for pole-all driver, and the green one is for round-robin driver. We can see that the throughput in case of pole-all driver was significantly better, while the influence on the background traffic was still acceptable. And here is another scenario of tests. In this case, values again two independent paths, but the background traffic was injected into both of them. The background traffic overlapped. For the first pass, the traffic started in second 3 and stopped in second 8. In the second pass, the started in second 7 and stopped in second 10. So we again see that the pole driver is significantly better than the round-robin driver, and the total throughput was really high in this configuration. To summarize features of PSOC library, PSOC library can be easily introduced into existing application, as it is another kind of sockets. PSOC library is configurable, and it allows to select select the driver for data multiplexing. That can be implemented also in other drivers. It is open in this way. The interface is prepared for other drivers. And the PSOC library allows to utilize the available bandwidth, even in case the bandwidth is varying in time. So it's all. You can find information at this address. It is also possible to download the current version of PSOC, and the part of that downloaded package are also some examples, so you can see how easy or difficult is implementation of PSOC in any application.
You have time for one or two questions? No question. So there is one for me. So you need PSOC library on both source and destination, obviously.
Definitely.
Yes.
Yeah, but you need on both destination, but you don't need to any patch to the drive to the kernel. You don't need any change on in the network. The only you need is PSOC on both sides.
But the problem is you have to know that the destination host has PSOC. There's no mechanism to find out.
Yeah.
Okay. And the stuff for download, is it just for Linux or for what kind of platform?
It is on Linux only. Yeah.
Okay. Thank you. Okay, so our last speaker today is that one, Andrew. He's from Australia, actually. He made his university degrees in Australia and worked there as well till last year. Since 2005, he's with Caltech in the US. The floor is yours.
Okay. Hello? Oh, it's loud. Okay. I'm going to be talking about the WAN Lab project, which Stephen Lowe has been instigating jointly with his co-PIs, John Doyle and Harvey Newman. And there's a whole team of us working on actually getting the whole thing working and using it and stuff. I'll start by describing what WAN Lab is and why we bothered building it, and tell you a bit about who's using it. And then I'll say a little bit about the equipment that we're using to implement WAN Lab and how that equipment's configured and where we're heading in terms of connecting to external networks, WAN outside of lab, and what we're planning on doing with the network. And by the end of the talk, I hope that there'll be somebody who's interested in actually using this infrastructure, and so I'll say how to use it. So what is WAN Lab? Like the name suggests, it's a wide area network, but it's geographically concentrated. It's all in one laboratory. What makes it a wide area network? The fact that we've got real fibre delay instead of using dummy nets and NIST and such like. We've got real carrier class routers, some courtesy or some donated by Cisco, others generously discounted by Cisco, and yeah, real servers, real fibre, real ONSs and such like. So it's a real network. We're trying to keep everything as realistic as possible given the budget constraints, but by being located in a single laboratory, it makes it a lot easier to control and such like. So that's the what. The why. Basically, there was a gap that Stephen saw. There's a sort of a spectrum of tools all the way from mathematical analysis and through simulation, NS2 and such like, and again using things like DummyNet and NISTnet and such like. Each of these is a stage more expensive to implement and a stage less abstract. You can simulate more details than you can analyse. You can actually have timing and such like of the protocols if you're using DummyNet and NISTnet and such like. And then at the far extreme, there's real networks like ultralight, checklight, all the big wide area networks. But there's a bit of a gap in scale between emulation, which is not really running on real routers, and running on a big, expensive network where you need to compete with a lot of other users for time and such like. And so Stephen built up this WAN Lab so that it can be used not to replace any of the other techniques, but just sort of to fill in the gap between what you can't do with emulation and what you don't necessarily need to tie up time on a real network for. So the aim is to be a wind tunnel for networking. It's the test bed where you try out scale models, essentially, of a network. We've got links from 2.5 gig, well actually from lower than that, from 1 gig to up to 10 gigabits per second. And we can get delays from back-to-back connections up to about 120 milliseconds. The idea was that it was going to be all configurable and evolvable. The modular design of it is trying to allow it to stay up to date. As new components come in, we'll be able to plug out the old ones and plug in the new ones. And the aim is to be as configurable as possible, like I said. We don't need to worry about breaking somebody's production traffic, so it's much more configurable than a real network. We can try experimental protocols without doing any damage to, like I said, to people's production traffic and such like. And so it's got, hopefully, most of the benefits of an emulated network, while staying a real network. Being all in a single lab, we can do a lot more things like passive monitoring. We can actually go to the routers and we can plug devices in either side of them and such like. And we had a lot of plans of doing active queue management, and currently one of the most, the projects which is used at most is actually an AQM protocol that we're testing. And like I said, it's part of a continuum of tools. It's also part of a continuum of the design process for protocols. Stephen did a lot of good theory way back in the late 90s, and then from that theory, he developed a protocol. From that protocol, they've developed a product. And that development is one of the things that WAN and Lab is aiming to promote. If other people come up with good theory, like Doug's doing very good theory, Doug's come up with a protocol, Doug's come up with a product, he's testing it on his own network, but I'm hoping to convince him to test it on ours as well. So if anyone's interested in developing protocols, the idea of having this is it's a transition step between implementing it in a dummy net sort of toy environment, and it might not be ready to let loose onto a full-scale network. And so WAN and Lab's a good place to test it, a good sandpit if you like. And it's going to be a global resource, like I was saying, open to be shared by everybody, and also connected to the ultralight run by Harvey Newman. Okay, so there are a few projects that are using WAN and Lab so far. There are 3 of them that are internal to the NetLab, which is Steve Lowe's group. One of them is TCB benchmarking, which is just about to happen in NetAir now. And the other 2 are actually have been used. It's been used for testing fast, which Doug's mentioned. It's a delay-based protocol, which avoids a lot of the problems of ADSL links building up 4 second round trip times. Fast aims to reduce all that. And it was the original motivation for WAN in Lab, and it's been successfully tested on WAN in Lab. And the other project which has taken a lot of time is MaxNet, which is an explicit signalling AQM type of congestion control scheme. And yeah, we've also got a few external people who are using parts of WAN in Lab or talking about using parts of WAN in Lab. One of them is from Computer Science Department of Caltech itself. Mojave FS is a new distributed file system which has been using some of the facilities. We're talking with some people from the University of Pittsburgh to look at TCP with small buffers, see what happens if you dimension your buffers very, very much smaller than people are normally doing. They've got some techniques which will hopefully enhance it rather than relying purely on statistical multiplexing. And the University of Melbourne, back home where I came from, there's a bunch of people there who are looking at single-bit congestion marking, like souped-up ECN coding. So that's who's using the WAN in Lab. Now, just as an example, MaxNet is the project which has used WAN in Lab the most. It's a simple 2-link topology we've been doing all the tests on. You can see we've got real routers with real links between them, but all of the fun stuff happens in the 2 software routers because it's an AQM scheme, and we can't control the Cisco routers yet, unfortunately. We can't program the cards and such like, so we're doing everything into into Linux software routers. And yeah, we're transferring data from hosts A, B, and C to a single listening server. And this is just an example. The thing I was going to show and be very excited about is showing that we're getting realistic delays at rates up to about 1 gigabit per second, which is faster than you can typically get on dummy net. Although Doug stole my thunder a bit by showing rates very high on a dummy net, almost up to 1 gig. But, so this is just nothing particularly fancy. This is just showing how MaxNet responds to UDP. Okay, so what is WAN in Lab? WAN in Lab consists of 4 Cisco 7609 routers. Each of them's got an OC48 line card, so that gives us 2 links. We've also got 6 15454 ONSs and a few dozen high-speed servers hanging off the edges to feed data to them. We've also got a 1 gig switch to save us from plugging everything in and out all the time. And we've got a Caliant switch so that we can switch OC48 links in and out to vary the delays. And speaking of delays, they're provided by 2,400 kilometres of optical fibre, complete with amplifiers, dispersion compensation, blah, blah, blah. This is a real wide area network just located in a lab. So we can get, using the 2,400 kilometres, we can get an aggregate delay of 63 milliseconds. And we can have up to 2 hops because of the 4 line cards. I mentioned earlier that we can get 120 milliseconds of delay. We can do that using IP loopbacks to pass over the 63 milliseconds twice. Okay, so that's what's in WAN in Lab itself, but very much part of the plan from the outset was to connect WAN in Lab to ultralight, which is just another high-speed test bed, which is a real wide area network. It's a 10 gigabit per second system mostly, with a few lower speed links. It's aiming to carry high energy physics data, so particle accelerator data and such like. And the purpose of the connection is to allow smooth migration of the protocols. They can be tested and developed on WAN in lab, and then gradually move to more and more nodes of ultralight as they show themselves to be stable. This collaboration is beneficial to WAN in lab because we get longer delays than we can get without the extra wide area network. We also get realistic jitter because WAN in lab suffers the same problem that all artificial networks suffer. We know exactly what the routers are there. We don't have all the uncertainties and such like that come with real networks. So having the connection to ultralight will give us real jitter, and also it'll give us the option of having real cross traffic. The benefit to ultralight is that by routing data through WAN in lab, they'll be able to make use of all the measurement infrastructure that will be part of that WAN in lab. Okay, so that's what it is, that's what it's used for. Now some of the technical details of how we do it. I was mentioning there's 2,400 kilometres of fibre. I was mentioning we get 63 milliseconds of delay. If anyone's done the sums, they'll find out that that's a lot more delay than you expect from 2,000 kilometres. The reason that is the case is we get each of the signals traverses the fibre 16 times. We have 4 WDM wavelengths. Each of those wavelengths carries an OC192, 10 gig, but we multiplex 4 OC48 streams onto that. So that gives us a total of 16 times traversing the fibres. With all these wavelengths and OC48s, we have a lot of transponders. So to reduce that a little bit, we have amplifiers whenever we can, and so we get 200 kilometre hops from our spools. Okay, so this is just a demonstration of what happens to a packet. It goes in, then it goes through the amplifier down to the other side. Then at the far end of the connection, there's a loop back, and it goes back. And then it goes on to the next slot of the same wavelength, and so on and so forth until it gets to the end and traverses 16 lots of the 200 kilometres from 2 bidirectional spools of 100 kilometres. Okay, so that's how we achieve the long delays, but to be configurable, to be flexible, we need to have variable delays. So the only way you can vary the delay in a network is by varying the length of fibre that's traversed. So we have a Caliant optical switch which selects the required number of hops. Some of them are just switched out and idle. And we have different hops of lengths 200 kilometres up to 1600 kilometres because our switch doesn't have an infinite number of ports. We can't have 200 kilometre segments being switched in and out all the time. We need to get a compromise between granularity and total delay. Okay, so where are we heading from here? One of the things I'd like to do is get better control over the capacities and buffers. Some preliminary experiments I've been doing indicate there's some buffering that's happening somewhere in the network that I haven't entirely tracked down yet. So we're getting 2 milliseconds worth of delay when I'm setting all the buffers I can find to 0. So one of the things I'd like to do is understand the hardware I'm playing with. Another thing that we're looking at is how best to saturate the links. Currently we're feeding the 2.5 gig links with 1 gig servers. So we need either to have 3 or more servers or to waste our 2.5 gig of bandwidth and artificially throttle it. Which is in itself a useful thing to do because one thing we can get to study with this is how does a router's token bucket bandwidth limiting quality of service measure, how does that compare with a real ideal channel of that capacity? Another thing that's important is to find creative ways to emulate more topologies. We've been fairly creative in getting long delays from our fibres, but we're still stuck with 2 links so far. So one thing that would be very nice to do is be able to expand that a little bit more and see how we can emulate more topologies. And cross-traffic generation, one of the most important aspects of a real network, which WAN in Lab is aiming to be, is the real network carries real traffic. So I think it's important that we have the most realistic cross-traffic generation we can for our benchmarking and such like. Currently we've got Harpoon installed, which is sort of state of the art, but not beyond state of the art. So I'm continually looking for better cross-traffic generators. If somebody knows some source, then I'd be very interested to hear about it. And also we're looking at better traffic monitoring facilities in the network. Okay, so by now I'm hoping that there are some people who are desperately keen to use WAN in Lab. Perhaps that's a vain hope. If anyone's interested, then please contact me. And at the moment we've got more time capacity on the network than we have users for it. We don't have any fancy infrastructure for time sharing or anything. If there are two users who want to use it at the same time, only one can run experiments, but other people can set up their experiments while some users are running experiments. And the software to run the system is still being developed. The hardware is fairly static now, but the software setup is changing. So if anyone has any application they would think it would be really nifty if you could do this, can you? Then come and tell us and we might be able to tailor our software infrastructure to meet your needs. So in conclusion, WAN in Lab seeks to fill a gap between emulation on one hand and live network experiments on multi-million-dollar networks on the other hand. It tries to be as realistic as possible given the budget constraints. We've got reasonably long links. We've got a simple topology as the trade-off of that. And the focus of our own research using WAN in Lab is going to be on TCP benchmarking, hoping to leverage off a lot of Doug's experience and see what we can do with that. And we encourage other people to use it either for submitting protocols to be benchmarked or coming up with other applications they'd like to use WAN in Lab for. Thank you.
Thank you very much, Rafa. Any questions? We are running time, so please bring your questions. Questions, please.
This is for you or any of the other two speakers. All the presentations had to do with optimizing use of higher speed packet networks. But if one were to install it and just blindly use, what is available today without taking these special measures, it's not optimal, but is it a noticeable improvement? Improvement up to a point where it gets worse, or what?
I think that's related to what Doug was saying. If I understand your question correctly, it's very related to what Doug was saying. If you just take a Linux box a Linux system out of the box, you'll get very shocking performance. But it can be with 3 or 4 simple commands, you can get 100 times the performance, which is respectable, although not blinding. Does that answer your question? Thank you.
I don't have a full list of parameters, but what kind of control do you have over the transmission circuits? For example, can you alter the MTU on ports and so on?
Yes, to a limited degree you can. You can certainly change the MTU on... wonderful, thank you. You can change the MTU on most of the Ethernet cards that we've got. You can also change it on the routers. Some of the things are going through a switch, and I haven't tried changing the MTU on that. I'm not sure if you can or not, but some of the things are hardwired from server to router, so those ones we certainly could change the MTU. Are there any other parameters you'd be interested in changing?
No, that's a good example.
Okay. Another example that just comes to mind is the ring buffers. One of my colleagues was just doing some experiments and was finding a lot of ACKs were being lost. After a packet loss, there was a huge burst of ACKs, and a lot of those were being lost. And so that's, again, something that you can configure with this framework.
Any more questions?
Packet loss. So how do you plan to introduce packet loss? in the system, because the poor performance of TCP comes from packet loss. And how do you plan to do it in a controlled way?
That's a very good question. One of the things I was thinking of doing is just the simple NIST-net approach. My theory was that a receiver's got to receive the packets, so implementing random packet dropping at the receiver shouldn't be an excessive computational burden. So it's not like running a dummy net where you need to input the packets and output them and have them going extra times across the bus. So I think that just software packet dropping should be reasonable. The other thing that comes to mind is the purpose of this experiment was, or the purpose of building WAN Lab was to look at fast, which is not so dependent on packet loss. So obviously we need to see how it works with packet loss, and that's one of the strong selling points that they're advocating about fast, the fact that because it doesn't depend on packet loss to indicate congestion, it can be a lot more robust against spurious packet loss. All of the experiments they've done so far have just been using a dummy net, so rather than using the optical links. Yeah, I've been toying with all sorts of harebrained ideas like detuning the links and putting fingerprints over the fives and things like that. It's not a particularly controllable sort of thing, so I haven't actually done any of that yet. But yes, it's something that's sort of under consideration. Thank you.
Any more questions? Okay, this ends this session today. I thank you all for coming, and especially thanks to the speakers. For the audience, there is a feedback form online. Please use it and give your feedback. Next event today is the opening session at 7 o'clock. Goodbye, everybody.